Okay, thanks. Well, yeah, thanks everybody for coming to my talk. We're gonna be talking about one of these SIMIODE modeling scenarios that I developed. I guess it was a couple years ago, but I've been kind of improving on it for the last 2 or 3 years, I guess. Anyway, we develop a model for free fall with air resistance. Usually these models are those types of projectile motion models. You always neglect air resistance. But I wanted to see, what we could do with, an actual model where air resistance was factored in. And we look at then predicting the assent time for a dart, a Nerf dart. So let me get into it here. The scenario specifically is, I guess, this 4-039S. It's called falling darts. Of course, there's a teacher version and a student version that you can look up on the SIMIODE site. So yeah, here's the overview. First of all, students are going to derive a second order nonhomogeneous eventually model of free fall that incorporates air resistance. I'll get into the details of that in a minute. Then they solve the model using two different methods, the reduction of order and separation of variables, and then undetermined coefficients. So I guess they can either use both of those methods, or you can just pick one of the two and just use one method. Either way. But then, yeah, they're going to predict the terminal velocity of the dart, or I guess just in general, any object, and the maximum height. So we're assuming this thing is fired upwards initially. So it's going to go up, reach a maximum height, turn around and come back down. And then they actually parameterize the model through experiments with the dart launcher. And then they'll validate the model also by going outside and then actually firing the darts up into the air and timing the ascent time to see how good their approximation was, or how good their prediction was. So yeah, I usually started out by talking about Galileo's law for free fall in the absence of air resistance. Two bodies are going to fall at the same rate, independent of their mass. And then I show this video of, I don't remember which Apollo mission it was, I think 15, where one of the astronauts brought a hammer and a feather up there and dropped them at the same time. And you can see they hit the ground at the same time. Pretty cool. And then there's a more modern version of that experiment at this, I guess, whatever this YouTube channel is, where they're in a giant vacuum chamber and they do the same thing. I guess it's with the bowling ball and a feather, but either way, you can see them hit the ground at the same time. So, okay, you don't need much. You need dart guns, but these things are like $2. So pretty cheap dart guns. Tape measure and video camera. Of course, everybody has that capability on your cell phone. So that's not too much to ask. Students get to use their phones in class. So yeah, the model. It's we start with a standard free body diagram for an object in free fall. You got the two forces, gravitational force and the drag force. And I explain a little bit about what happens when the object's falling. Eventually the drag force, which is always opposite the motion, in the opposite direction of the motion, eventually it equals the gravitational force, and then you just have no acceleration. The object falls at the same rate it had when it reached that terminal velocity. And I usually ask them, like, what is that velocity? And some of them will shout out, that's terminal velocity. So anyway, yeah, from the free body diagram and throwing in some derivatives, you get the second order differential equation that involves, of course, acceleration due to gravity, g, but also a drag coefficient, k. I don't set them off solving that differential equation right off the bat. I give them just like a practice problem with numbers in place of the parameters, just to get their feet wet. And they're always, it's always easier for them to start with a differential equation that just has the two variables and no other parameters. So yeah, two methods. The first one is we reduce the order by noting that the velocity is the first derivative of position. So y is, by the way, the height of the object. And And so, yeah, then you can substitute v and v prime into that equation for y prime and y double prime. So you get just a first order equation that is separable. So they do the whole separate and integrate process. I give them an initial condition for the velocity so that they can get a particular solution. Then we look at long-term velocity. So we take the limit as t goes to infinity. And again, I ask them at this point, okay, so what is the meaning of that limit? And they can usually tell me, oh, that's terminal velocity. So yeah, I have them graph the solution, and you can see the velocity approaching that terminal velocity, the limit. And then they integrate back up to the position function, so they actually get y of t. And then we just assume the object is fired from the ground, so initial height is 0, so that they can get a particular solution, and then they graph that also. And then you get an idea of what the height in time curve looks like. You can see it has a maximum value. Then that's the important part. We want to determine that maximum value, because eventually we're going to test our predictions by timing an actual dart fired up into the air, and we time the ascent time. So that if you can see at the 0.805 seconds, that's the ascent time with these particular parameters anyway, with this practice problem. So yeah, anyway, they set the velocity equal to 0 and solve for t to get that. Determine the maximum value. Okay, and then the second method, this is method of undetermined coefficients. So it's roughly the same process, other than, a different method for solving the differential equation. Give them the same initial conditions. They get a particular solution. Determine the max height again, and then take a look at the limit of the velocity. Now, after they have to take the derivative of their solution first, and then take the limit to get the terminal velocity. And then they graph the velocity again and graph their position function. So kind of the same idea as the first method. So now we go back to the original model with the parameters in there, the unknown parameters. Well, I guess it's just k is unknown, g is acceleration due to gravity. So it's all the same process. Initial velocity, though, we denote by v naught. And I have them denote the limit of the velocity function by v sub t. Again, ask them, oh, what does that mean in the context of free fall? And by this point, they know it's the terminal velocity. Why we use it. That's why we use a subscript t. Graph the solutions, or graph the solution for the velocity. And then they integrate up to get their position function. Find the particular solution, graph the particular solution. So same stuff that happened in the practice problem. It's just now they have that parameter k, and you can graph this stuff in Desmos, and then you use a slider for the drag coefficient parameter k. So you can see the shape of the curve changing. And I was actually going to bring that up. I'm not sure if I'd be able to easily here. Yeah, I guess there it is. So yeah, there's a parameter for the drag coefficient k. When k is 0, you essentially have the standard model with no air resistance, just a parabola, quadratic model for the height, straight line for velocity. But then as you increase the drag parameter, you can see how the velocity curve changes and how the height curve changes relative to the no air resistance model. Okay, so anyway, so then we do the same thing. Second method, undetermined coefficients, but with the parameters in there, so not a practice problem anymore. Look at terminal velocity. Okay, so finally here, we're going to estimate the terminal velocity and the muzzle velocity, because we got to know the initial velocity, how fast the dart is moving when it comes out of the gun. So for the terminal velocity, all right, so basically this is what we do. These are usually done with groups of students. So each group will have their own dart gun. We'll go outside if it's nice enough. Otherwise, you can do this inside if you have a like a really high stairwell, or some room with a really high ceiling. Somehow we make that part work. So anyway, you fire the dart straight up. Oh, and I guess I have a video here. So fire that dart up in the air. You're taking a video the whole time. So students are taking video here. And what we're really concerned with here is when it's coming back down, we're assuming the dart is, oh, must have missed it. Assuming it has already reached terminal velocity by the time it comes back into the video frame on its way down. And you can verify that. So if you look at each frame, when the dart first comes into view, and then the next frame after that, you can see where it is after that, and then another frame, you can see it's fallen by the same distance. So from that you conclude, oh yeah, it must be effectively it's at its terminal velocity. And so I use VLC video viewer for this because there's just an easy, you just press the E key to advance frame by frame. I'm sure you can do this in other programs too, but so we get these frames and we know the frame rate for the video. So standard frame rate is 30 frames per second. So that the time between each frame is 1/30th of a second. And what we do is count the number of bricks really that the dart has fallen by. And then we measure the thickness of the bricks and including order. So we get an idea of how far it's fallen each time. And so then it's just, velocity equals distance fallen per time to get an estimate of the terminal velocity. So this is just an example calculation here. It's kind of the same idea for the muzzle velocity, except they fire the dart horizontally this time, but they're taking video. I'm not sure if that's a video or not, but no. Anyway, so they take video of the dart fired horizontally. We know the length of the brick, we measure that. And then you just analyze the frames again, see how far the dart travels in one frame. You get the velocity. Okay, so once you have the muzzle velocity, sort of go back and forth here, that becomes your V naught in the model. And then the terminal velocity, that becomes your V sub T when we had taken the limit earlier. And the formula for the terminal velocity involves the drag coefficient. That's the thing. We can predict you can determine the drag coefficient value using the terminal velocity. Okay, so then predicting the ascent time. So this is just setting the velocity function equal to 0 and finding the time it takes to reach max height. And now these calculations involve initial velocity and the terminal velocity. And once we have measured those, you can throw them in to get an actual prediction of the ascent time. And then we go outside and actually test that prediction. So we're kind of validating the model this way. So students will go outside, fire the dart directly upwards, and they're timing how long it takes just to get to the top of its flight path or trajectory. So they fired it up, timing how long it takes to get to the top. They do it a bunch of times and kind of get an average, just to average out the errors. Yeah, and then they're calculating relative error. So they're comparing their prediction to what they observed through the experiment and getting a relative error. Usually they're pretty close. Over the years I've been doing this, they usually get a pretty small relative error on this. So that's nice. It's fun to watch them, see, oh, this is what we predicted, and that's not exactly, but that's really close to what actually happens out in the real world when they fire the dart. Okay, and then there's this one last optional bit that I have where they can compare the model that incorporates air resistance, so the main topic for this whole project. They compare that with the model that ignores air resistance. I kind of showed the decimal stuff relating to that earlier. Anyway, so it's just the standard model that does not worry about air resistance. We solve that one, and the idea is in our model, we want to let the drag coefficient go to 0. and it should equal, so let me get the Desmos thing up here again. It's easier to explain with all of that. There it is. So yeah, so you can see the solid curves here are for the model that's actually they're working on in this module. So there are solutions there with the drag parameter, and you can see if you let that go to 0, those curves are approaching what you get when you just start off by assuming no air resistance, right? The parabola for the height and the straight line for the velocity. And I do have the actual solutions here. So in this last part of the project, we want to, actually use these solutions to prove that as k goes to 0, you just get a quadratic. But that's not very easy here because you have k's in the denominator. So what they end up having to do is expand this exponential piece in the solution using Taylor series. And then it becomes more obvious. A bunch of the k's cancel out from the denominator, and you can just let k go to 0. And what happens is you get just the standard quadratic model, -1/2 gt squared plus v naught t. So that's that. See if I missed anything there. Taylor series stuff. Yep, k goes 0. Yep. Okay, so that's the end of the project. I guess that's the end of the talk. Does anybody have any questions?
So I have a question. I think
Yep.
that you used linear air resistance in your model.
Oh, yeah,
That
we did. Yep.
Yeah. I've done projects like this, and I've used like second order air resistance, and then you solve it numerically.
So like
Like V squared.
drag force is proportional to v squared, you mean?
Yeah.
Yeah,
Yeah.
okay.
And the way I tested that was I had my students build a like a pendulum thing, and they at the end of a rope they put like a tennis ball, and then they
Sure.
let the thing swing back and forth because I figured we can control that better. The first idea was to shoot something in the air like you did, and then I figured that's going to be like horrible to try to actually measure it.
Yeah.
And then what we did was we recorded the tennis ball swinging back and forth. And then we did use some sort of image processing program to actually sort of, I don't know, quantify that. And then
Sure.
we matched it up with a numerical solution. And it was like amazing that it matched up like really, really closely. It was like, I couldn't believe it. But it's a really good project what you did. I like that you did it like sort of like low tech. I like that. That's
Yeah,
awesome.
I just wanted to be easily accessible. I'd be curious to have a look at your projects if you will be willing to
Sure.
send that to me.
Right now I'm in my car, but when I'm at home, I'll send it
Sure.
to you.
Oh,
Yeah,
okay, yeah, great.
yeah.
Thank you. I guess there's a question from Robert.
Yeah. So I'm a high school teacher, and from time to time, when there's enough students, I get to teach differential equations to really high performing seniors.
Yeah.
So
Okay.
my question is, how much time does this take when you do this?
Oh, I should have.
I mean, it's
mentioned
really great, but how much time do I need to plan for this?
Yeah. So I guess if you get familiar with it, acquainted with it ahead of time, you can see that you can stretch it or compress it. I mean, there's the practice problems that you would not have to do if you want to shorten this up. And there's the 2 methods. You could just choose to do only one of the methods to solve the differential equations. There's the final bit where you're doing the asymptotics kind of stuff with, seeing if the air resistance model approaches the non-air resistance model with Taylor series and all that. You can skip that if you want to make it short, but if you did all of it, this takes me, let's take about 3 50-minute class periods. So it's like a week for a 3-credit course where I'm at anyway.
So that's not bad.
Yeah,
So
no,
for
not
me,
too. I mean, maybe it'll run over to the next week sometimes. but
yeah.
we-
Well,
yeah.
yeah, I have an advantage. I'm given a year more or less to do a semester class, so I have a lot of
Hmm.
freedom to
Oh, okay, yeah, nice.
to even let the students just run with things. But I think I might try and steal that the v squared pendulum notion, because that
Mhm.
wouldn't be terribly that wouldn't be a stretch. Well, I mean, it would challenge my students, but it would be within their. We
Yeah,
could
I'm,
do
I'm
that.
also
Yeah.
curious to see how that would. I mean, I've thought about the second order air resistance stuff in other class under other contexts, and oddly enough, I never thought to bring that into this particular project. So now I'm going to
Well,
look at that.
well, yours is good because they can actually like analytically solve it. Where when you
True.
have, I think, nonlinear air resistance, then you end up having to like do Euler's method or something
Yep.
with them, which is something that's really cool. I like that, but it's like you're going in a different direction.
Yeah, yeah, and I do this in my differential equations class, of course, but I also do this in a math modeling course where
Mm-hmm.
differential equations isn't, you don't have, it's not a prerequisite.
Mm-hmm.
So assuming they've done separation of variables, at least in like a calculus, calc 2 or something, they can just look at that one method. Or if it's a situation where they don't know how to solve analytically those equations, I just give them the solutions, and you can still
Mm-hmm.
do all this other stuff with the project. All right, it's not a differential equations project anymore, but it's still a modeling project.
Mm-hmm.
It's still a parameterization with experiment type of thing.
Yeah, I like the way you do it. I'm going to give it to my students this semester actually, because I want them to have like examples of like separable differential equations and things like
Hmm.
that are applied. So I like that. One thing I was thinking of doing was doing it with balloons, like helium balloons or something, or even regular balloons. But I
Oh
never,
yeah,
but again, I never got around to doing that. Have you thought of using balloons for something like this?
had not thought of that. Now I'm thinking of it though.
Because you get a lot of air resistance with the balloons, right? You know, they go
Yeah,
like they have very little mass and they have a lot of volume. So
yeah, definitely. Yeah, that is something to think about. Hmm.
Let me ask, I was thinking about drag proportional to velocity squared all the time, but I wouldn't imagine pendulum. I was thinking parachute, but I do not know. Imaginary no wind situation, do you think it would work?
In a no wind situation.
So instead of balloon or pendulum, would something like parachute work?
Oh, sure. Yeah. I mean,
When you started your
I-
presentation,
well,
I immediately started thinking about it, but I do not know if it will work. I never tried.
yeah, no, that's another thing to think about. You probably have to make some kind of, contraption with a parachute. I'm talking about
It is
actually jumping out
definitely
of a plane. That would be
proportional to
fun.
second order velocity. I just don't know how is it works.
yeah, well,
You
when you
would-
use these models, you have a coefficient of drag. You can go online and you can they've calculated this for different shapes, but I
Mhm.
don't know if you can find one easily for a parachute. Then part of the project would be actually calculating the coefficient of drag, from the experimental data. But that's a good idea also, right? I like
Yeah,
it.
yeah, you'd think that would be the kind of the idea, predicting the drag coefficient
Mhm.
for the parachute. Yeah. Mhm.
Yeah, that's a really another good idea, like to do it for that.
Yeah, yeah, yeah. I guess there's all kinds of ways you could
Mhm.
augment this thing. Yeah, I know the students like playing with the dart guns, so there is that. Just like getting to shoot them up into the air and at each other here and there. But
So do you supply the dart guns for the students and the darts?
Yeah, I just have a bunch of them in my office that I've
Uh-huh.
accumulated over the years. But like I said, they're pretty cheap. I get
Mm-hmm.
paid $2, $1 or $2 for one at Walmart or something.
And you shoot them up and you want the thing to reach the terminal velocity. That's like a big part of the project.
Yep.
Okay.
Yeah, so you got to make sure that you have to make sure that the weather's okay. I mean, I'm in Minnesota, so this is hard to do in the winter when it's like really cold or snowy or something, but I have done it in stairwells. But you need to have some kind of way of measuring the distance as it's falling. It's convenient to have a brick wall there. But I have done it where there's just a tape measure vertically, but you have to just be careful. You have to have good aim with the dart so that it comes down next to the tape measure so you can see how far it's going each frame, each of the video frames.
Yeah, I wasn't able to watch a whole presentation because, like I said, I'm in my car. If you just are able to figure out what the terminal velocity, can you calculate the coefficient of drag from that?
Yep, you can get that right there. I don't remember off the top of my head what it is, but I think it's just involves the terminal velocity formula that they derive involves the drag coefficient and the mass, maybe,
Right.
or G, just G, I think.
Mm-hmm. Okay. And
Yep.
like, about how far does it have to do these darts have to fall in order for them to reach the terminal velocity?
They usually go about, I'm just guessing here, oh, man, about 40 feet into the air, 40, 50 feet.
Okay, so you have to do it outside.
Yeah, yep. And like I said, unless you have a really high stairwell
Oh, that's a good idea.
or a gymnasium or something.
Or like a big auditorium or something, maybe
Yep.
it might work.
Yeah, if you can find a spot like that in, wherever you are. I mean,
Yeah, I'm gonna do that. I think my students will like it. A lot of them are like engineering majors and stuff. So I think they'll really like playing with the dart guns, but more than the balloons, actually. I think they'll
yeah,
like that.
yeah, the same situation with I have a lot of engineering students. So yeah, they enjoy it.
All right. Thank you so much, guys. We're like 2 minutes over time, so I'll go ahead and end the meeting. Thank you so much, and enjoy the rest of the day.
Yeah, thank you.
Okay. Thank you, and I'll remember to send the work on the
Oh.
nonlinear stuff to you.
Yes. Yeah, that'd be
Take care
great.
now. My name's Chris McCarthy, by the way. All right, bye-bye.
Okay, yeah, nice to meet you. Thanks.
Nice to meet you.
Bye.